Bismillahirrahmanirrahim. Greetings. The context of this video lecture is an introductory to a mini series of 2 or 3 video lectures about the concept of implicit differentiation. Now, in this lecture, I'm going to give an overall picture of what implicit differentiation is all about, and also about the motive behind that, and also about some of its benefit and application. Now, in the videos to come, I will be going through application and solve problems. So let's get started with the motive of behind the implicit differentiation. Now, the rules of calculus in general and differential calculus in particular applies to single valued functions of single variable. I repeat myself, the rules of calculus applies to single valued functions of single variable. But there are quite many relations that they do not define functions. Like those that we are familiar with, like equation of circle, like equation of ellipse, equation of hyperbola, or equation of y squared equal to x ellipse, the parabola, yx squared equal to x parabola. Now those relations, they do not define functions. Now the graph, the analytical geometric graph of them that I have put them in here for the demonstration, we are familiar from the high school that we said the vertical line fails. As you can see here for this, in the case of circle, the vertical line that we are familiar will fail. So this cannot be graph of what? Graph of a function. But if we cut this curve, this circle, from this point, they call it branch point. Of course, this has a point, you know, in the subject of this is a little bit going to be more complicated and goes to the complex variable. These points that they cut, the curve, that they do not represent multi-valued function curves. Those points that they cut them, they are called branch point. But that, again, I repeat myself, that belongs to upper level courses in mathematics, in senior level or a graduate level, in a complex variable go over them. But here we are not going to go, that's way, way beyond the scope of this lecture or even calculus lecture. So here, as you can notice, here, this branch, the vertical line pass, as I have drawn it separately, we can see that. And also if you go and for this one, the lower branch of that, also the vertical line pass. Is that right? Now, this motivates the idea that if we can do it geometrically, that we can do it also for the, I have the picture, in fact I put it up for you, for the parabola. If we can do it geometrically, can we also do it analytically? Because, you know, there is a very strong relation between geometry and analysis. So whatever we can do geometrically, we should be able to do it possibly analytically. Now let me, just for the sake of the discussion, let me also put the parabola, the y squared equal to x parabola. Now y squared equal to x parabola, as you know, the relation is not the function because geometrically the vertical line fails, as you can see that. But if you can cut it from the branch point is the point that most of the time that the graph is the derivative of that at that point geometrically is a slope of a tangent line is vertical, which means it's not defined. or the slope of the tangent line is parallel, which is the derivative at that point is 0. Those points, they call them usually the branch point. And in upper level courses, that's the point usually they cut the graph so that single valued function can be applied on them, and then we can investigate about the area under the curve, we can investigate about the derivative, etc. But again, I repeat myself, that is way beyond the scope of this lecture, or even in calculus course. Now if we can cut this one, I put my hand here, the upper hand of it, as you can see, this will pass so-called vertical line. The same is true with the lower part. We can cut it. Now, the point is that for this kind of curve that we are familiar with, to write them, the explicit form of them, so that y is a function of x, the single valued function of x, we don't really need to go and do that. Then we can cut them and do whatever we want to apply the rules of calculus. Now, by the way, I have this one if you want, just for those that they like to take notes. I keep it for a few seconds, and that is my parabola y squared equal to x parabola. And there are two branches, as you can see, I have derived of them. I'm doing that, all of them, but I'm doing that geometrically. So I want to relate this one to analytical situation. So analytically, if I can do it also. Now, now I have also other curves that I have this one. Let me put it on, if I may. That the curve of them is not as simple as and as nice as we know, like the graph of circle or ellipse or y squared equal to x parabola. Graphs like that. It's a multi-valued relation, multi-valued function is a relation. Now, as you can see, the vertical line definitely will fail. Now, at the point, as I already mentioned, we call them branch point, that the derivative here in this case is not defined. If we cut them into curves, you can see I have one curve here, 2, 3, 4. In this figure I have four curves that each of them, the vertical line will pass. Do you follow me? No. Can we also do that analytically? That's the point. Now, for some functions like, for some relation like circle and ellipse and y squared equal to x parabola, yes, we can do algebraic manipulation and write y as a function of x. We can do that very easy. Now, for example, as you can see here, x squared plus y squared equal to a squared is a equation of a circle. And from this equation, when we do algebraic manipulation, we can separate x and y and write y as a, in one of my videos lecture that if you get the opportunity, please watch them all. I do not say y equals to equal. I don't say y1 equals to f of x, but I read it the way that give me knowledge also inside. I say y is, this one I don't read it equal. I say y is a function of x. With the rule of correspondence between x and y to be this, which is a squared minus x squared, a square root of that. So I take the equation of the circle, and which is not a function, is a relation, and two explicit function can be derived out of it. By what? By simple algebraic manipulation. So I add to both sides negative x squared, is that right? Then I take a square root of both sides, and the square root of both sides will be plus or minus. The plus part of it will be the upper part of the circle, and the negative part of it that I have put it with a with highlighted with the green, with the yellow, will be what? Will be the lower part of the loop, or of the branch of circle. So the circle branch will be cut into two branches, upper and lower, and this is the analytical representation of that. We can do that for circle, we can do that for ellipse, we can do that for parabola. As a matter of fact, I have done it for also parabola, y square equal to x parabola. So I take a square root of both sides, and I end up with y is a function of x with the rule of correspondence to be a square root of x, and the other loop of it, the other branch of that, that I have shown it. Let me show it one more time. And the second one of that is what? Is this part, which is negative square root of x. This is what? This is analytical representation of the lower part of the parabola, y square equal to x parabola. Now, the point is that, what about other curves? Like for example this one, that I'm going to go in the videos to come, I'm going to go over these two problems. They're very interesting. And this one, if you do some very high school algebraic manipulation, add and subtract on both sides and try to solve it for y, you notice that you cannot separate y from x, so that y is explicitly function of x. The right hand side you will have x and y both involved. So you cannot, in other words, separate x and y. Do it very easily. Factor y out and take everything the other side, divide by what it comes there, and you end up with the equation cannot be written y as an explicit function of x. Now this is simple, you can do some simple arithmetic and do that. Now this curve is even more complicated. This is even more complicated. Now one suggestion you can have is that, okay, if it is complicated, what about if we hold x constant, then we will have a polynomial of degree 6 in terms of y. And go ahead and solve it. But then we have another problem. The problem is, for those of you who are familiar with Galois and Abel and the history of a polynomial, or hopefully you will be taking abstract algebra, you know that the polynomials of degree 5 and higher, there is no general formula to solve them. So even if we keep x fixed and try to solve it for y, we have a polynomial of degree 6, which according to the Galois theory, Galois theorem, is not solvable by radicals, we call it. Do you follow me? So we can do the same thing for x. Keeping y constant, then we have even bigger trouble. We have a polynomial of degree 8. And if it is more than 5, we have no general solution. As a matter of fact, if the polynomial is of degree 3 and 4, it is already too messy to write it. Only polynomial of degree 2, that we call it the quadratic formula we can use, is the simplest one that we are used to do it. But when you go from polynomial of degree 2 and 3 and 4, we do have formula, but it's very long and complicated and doesn't worth to go through the painful of that. And also, when we go to the degree of 5, I'm repeating myself, there is no general solution. So then question comes, what about if we are interested for the rate of change, excuse me, rate of change of this kind of curve at a certain point on the curve? Not that we know we cannot, but we cannot solve with x in terms of y or y in terms of x, and we are stuck with that. Why can't we do that? Now the answer is implicit differentiation. So by implicit differentiation, any point on this curve, we can find the rate of change of that analytically. But there are two conditions imposed on that, meaning that based on assumption of these two conditions are satisfied, then yes, we can go and do implicit differentiation and find the rate of change of these at that particular point. Isn't that interesting? And that is what the subject of implicit differentiation comes from. So in the next lecture, and next two lectures, let's say, I will be going over solving these two problems and see how implicit differentiation comes to our rescue, and he can tell us the rate of change of the relation without going through trying to break it down and finding explicit function of that, because they are multi-valued functions. Because still we use the word function, but it's not single valued function, which means the outcome of that is not single, this kind of curve. Like circle is a double valued function. So single valued function, I don't have to say what they mean, because the words themselves are really saying the meaning of the sentence, or really saying the concept of the statement in a sense. Single valued function and multi-valued function. So they are kind of multi-valued function, this curve, and so they are not function, in other words. So that the rules of calculus that we are used to cannot be applied. Okay then, I thank you for watching. That was an introductory lecture, and as always, I wish you all prosperity and good health, and please stay safe. So long.